So we started with sample proportions, and kind of here's the context in which we would use it. You might take a sample and find that in your sample that 20% of the people you sampled are obese. Actually, take that back, I said that wrong. This is telling you that your population, someone claims that 20% of our entire population is obese. So P equals 0.20. And that's just a plain old P. That's your population proportion. So 20% of Americans are obese. In your sample, you take a sample of 30 people, and 11 out of 30 of them are obese. And 11 out of 30 of these people, you get your people from the first 30 people that you see walking out of the mall. Okay? So your sample proportion, P with a little hat, 11 divided by 30, is 0.37. So your sample is definitely higher than the 0.20. Is it higher enough, then, is the question, to be significant? So then I follow this up with, how likely is it that this sample is a good sample for our general population? Was picking the 30 people, the first 30 people that walk out of a mall, was that random enough? We can all cut, and then everyone's degree of it, if it was random enough was what is fair. And then the question is, are we led to believe that there is some correlation between those who go to the mall more frequently and obesity? So maybe that was so much higher than the 20%, it was up to 37%, because there is some correlation between people who go to the mall are more likely to be obese. I don't know. You could say that's bogus, absolutely not, or maybe that's true. Maybe they're coming from the food court. I don't know. Okay? But that would be, this is where a simulation would come in. And we would find out how likely it was, or how coincidental that 37% was likely to be. Was it coincidental, or was it due to causation, or correlation, we should say, rather? So that's the big question when you run a simulation. What are the chances that this was a coincidental thing, and it could coincidentally happen within reason, or is there a correlation behind this? So you would run a simulation, and I think what you can't see is that your P would be 0.20. P equals 0.20. That's the population proportion. Your sample size is 30, and we're going to run 100 simulations. Okay, we're not going to actually do this, but what we're doing here is we're essentially saying, okay, if we know the population proportion is 20%, which we do, and we were to randomly take a sample size of 30 people 100 different times.
Is this piece minimal?
We only actually did it one time, and we got 0.37. But if we were to do that same experiment 100 times over, truly randomly from the entire population, we want to see how many of those simulations actually ended up with a population or a sample proportion over that 37, greater than or equal to that 37. If out of my 100 simulations, only 2 out of 100 were that high, I would say that this is not coincidental, that there's actually a correlation behind it. Okay, that maybe something about being a frequent shopper at the mall makes you more likely to be obese. Maybe there's some correlation there. Not necessarily causation, but maybe there's a correlation. On the flip side, if out of my simulations there were like 42 out of the 100 were that high, then it probably did happen by chance, and that one sample you grabbed just was by chance that high. So that, however many you get out of 100, that's your percentage of the time that this could happen coincidentally. So if it only could happen 2% of the time coincidentally, then it probably wasn't coincidental, which means 98% chance that there was a correlation. Versus if it happened 42% of the time, then this could have happened by chance 42% of the time, and then it very likely probably was a by chance sort of thing, and there's probably not a correlation. Okay? So, based on, and let's just pretend that we did this and we got 2%. 2% of the time our simulation was that high. So, when we're writing statements and we're writing or explaining conclusive statements, remember we're never going to use definites. We're going to say it is likely, very likely, unlikely, or very unlikely that the people leaving the mall are a good representation of the entire population. Since this number was so far off from the population proportion, I would say it's very unlikely that the people leaving the mall are a good representation of the entire general population. Because it appears that there's something about going to the mall that is correlating with people being obese. In the second, so another statement you could say is that it is blank, that there is something about those who go to the mall regularly that correlates with being more or less likely to be obese. So I would say it is very likely that there is something about those who go to the mall regularly that correlates with being more likely to be obese. It depends on what they're asking you to comment on. Sometimes they say, how likely is it that this is a good representation of the entire population? And maybe, back to our original question, maybe taking a sample of people leaving the mall, if you want that to represent your entire population, isn't a great idea. Maybe you should, again, something that would be totally random, maybe you should take Social Security numbers and collect 30 random Social Security numbers. Maybe that's how you should do it, because that would kind of minimize coincidence. Okay? Like I said, going to the mall, they may be coming from the food court. Who knows how many people run in the mall just to grab, I don't know. I didn't want to make this example anything as obvious as like, oh, the 30 people leaving the McDonald's drive-thru. Because that would be, you'd have some preconceived notions about that. So that's proportions, okay? Sample means. And now the context of this is going to be similar, but I wanted to point out how sample means are different than sample proportions. So here I know that the average weight of the adult female population is 150 pounds. So this is the population average. That's what that lowercase u means. So 150 pounds is the population. If the average weight of the first 30 women seen leaving the mall, so we're still taking and sampling the first 30 people leaving the mall, so that part of the experiment I kind of kept the same. It's not an experiment, actually. It's an observational survey. But instead of coming up with the proportion of them that are obese, I'm just coming up with the average weight of those 30 people. So the average weight of those people is 152 pounds. So my X bar is 152. Population proportion, population mean, sample mean. So my population's average weight is 150. My sample's average weight is 152. I want to pause there and make sure you understand the difference in those two observations. The first time, as the 30 people leave the mall, I'm asking them what their weight is, and then I'm saying yes or no. I'm really putting them into the yes obese category or not obese category. And then I find that 11 out of 30 are obese. The second one, I'm just taking all their weights and I'm averaging them together. So that's your difference between proportions and means. But then again, if the question is this significantly higher enough? Obviously the sample weight is higher by 2 pounds. Is that significant enough to conclude, again, that there's a correlation or not? So we would run a simulation with a population mean of 150. Your standard deviation would have to be given to you. So let's say I run a standard deviation of I don't know, 1.1, and a sample size of 30 again, and I'm going to run 100 simulations. And let's pretend that when I run this simulation and I'm given my list of sample means, let's pretend that 21 of them have a sample mean greater than or equal to 152. Now, this is a number and a percentage where you could go either way. It's all in how you explain yourself. So, again, come up with your answer as to whether or not you think this is a coincidental difference, or if you think it's significant enough, come up with your answer as to whether or not you think there's a correlation, and then sell it. So, on one hand, I could say, it is, let's say which way I would naturally go. It is, well, I could even be exact about it. There is a 21% chance that my sample mean is higher due to coincidence. And by coincidence, I mean sampling variability. It could just so happen, there's a 21% chance that your sample mean was higher just because of the luck of the draw of the 30 people that walked out of the mall first. But this means there is a 79% chance that it happened due to an actual correlation. Meaning there's something about those mall shoppers again that makes them a little bit heavier. Do we follow? So whatever percentage you get in your simulation, that's always the percentage chance that had of happening coincidentally. Okay, and if it's a very low chance, then it probably did not happen coincidentally, and therefore it happened due to a correlation. Are we clear there? Do we see the difference of those kind of same study-ish, but side by side, you can hopefully see the differences. Okay? The biggest takeaway is that when you're doing a proportion, you're literally just kind of checking the box for each of the 30 people. Yes, they're obese, or no, they're not. And you're coming up with the fraction of them that are obese and comparing it to the fraction of the population. When you're doing sample means, you're actually averaging together all of their weights for your sample mean and comparing that to the average weight of the entire population. Are we clear? Proportions versus averages. Cole.
I know how it sounds different, but I know we usually use the simulators online. How would this work for
So, and I'll show you. When we get here, you're not going to be able to run the simulation, but they're going to give you the diagram so that you would be able to see, okay, how many are above the 0.4 cutoff, and you grab your percentage from that. Okay? Last type of thing that we did, this was not an observation like the previous two were. This is an actual experiment. So the big things with experiments, we assign randomly into two groups. We're going to try to control the group so everything about the groups is exactly the same except for one feature. And that feature is usually what we hypothesize is the cause of any effects that we see. So I have 30 people again. I'm assigning 15 to live with no technology for a year and 15 to live with regular technology for a year. That means really by no technology what I was getting at is no phone, no TV. No cell phone, no TV, like no internet, okay? No internet, no TV. And they're all eating the same meal, so I'm going to try to control what they eat, because my study is going to be regarding weight loss. And I want to see if people who live with no technology versus people who live with technology have a different amount of weight loss. What's your thought on that? What would be the, maybe not the cause and the effect, but the correlation? Who do you think would, what am I getting at here? What about technology might play into weight loss? Right. If you don't have technology, you're not going to have as much to do. You might actually get up off the couch and go do something. You won't be stuck on your phone, stuck in front of the TV, stuck at a computer surfing the web. So the thought, maybe, from this scientist's perspective, is that if you have no technology, you got to get up and do something. Keep yourself entertained. Okay? So that might be what they're looking at. Now, the no-tech group, so people without technology, lost an average of 4 pounds. The people who had technology lost an average of 2 pounds. So the people without technology did lose more weight. Is it enough weight, though, for you to think that it was coincidental or actually caused by the treatment? Do you follow? So we would, and that's the question I posed, is this significant enough to suggest that living with no technology makes you more likely to lose weight? Or is this outcome potentially due to coincidence in how the people were grouped to begin with? So maybe, because there's always sampling variability, and even if everybody lived under the same conditions, we would have different weight losses for everybody. Okay? Maybe it just so happened that the way it was quote-unquote randomly done happened to put people who were more likely to lose weight already in the no-tech group. So we would run our simulation, and the biggest thing is to first find the difference in the observed sample mean. So my sample mean of 4 versus my sample mean of 2, and I say to take the no-tech minus the tech. So 4 minus 2 would be 2 pounds. And then you would run 100 simulations, where the simulator is going to take the 30 people and shuffle them all up, split them and spit them out into 2 groups of 15 randomly, and compare their averages and come up with their difference in averages, and then it's going to shuffle them all up, spit them out into 2 groups of 15 and find the difference in the averages there. It's going to do that 100 times over. What percentage of the simulations resulted in a difference in sample means of 2 pounds or more? So that's where you would look at something like this that was given to you and count up how many resulted in 2 pounds or more. Let's say that was only 3%. Again, whatever percentage you get, that's the chance that it had of happening coincidentally. So you would say there is a 3% chance that the 2 pound difference was due to coincidence in how the people were grouped. There is a 3% chance that the 2 pound difference was due to coincidence, which means there was a 97% chance that it was actually due to the treatment. And so most people would say, with a percentage that high, that there's a 97% chance that living without technology might actually help your chances of losing weight. And I think Anthony's hypothesis as to what that relationship would be is spot on. Okay? So, online you will find an entire review packet with like 20 questions.
Why are they only
Shh. Please don't interrupt me. These numbers 15, 16, 17, 18, and 19 are on that review sheet. I will make a video of me doing these and talking through these, and I will put that on there so that you could maybe try it on your own and check. And then there's like 14 other questions that you want to look at to help review for tomorrow, okay? But I would start with these 5, 1, 2, 3, 4, 5 questions, yeah. Jacob?
Why didn't you just print the packet?
Because the packet would have been 4 or 5 pages long.
No, right? I've done worse.